Testing, testing, testing. Good evening, fancy meat computers. There we go. Yep. Yeah, sorry about that. Yeah. I knew I was forgetting something, you know? Well, well, well. Oh, frick, I forgot the playlist. Ah! Okay. I'll do it now. Playlists. Um, I'll do it after the lecture. Sorry. Yeah. No, I didn't. I didn't show my password. Thank you. We are having in-person lectures for this class in a week. That is correct. Yes. So, yep. In-person classes start next week. After in-person classes have started, I will be video recording the lectures and then posting the lectures to YouTube after the lectures are complete. So, you should be able to if you have to miss the lecture for whatever reason, you can catch it online. Of course, in person is going to have higher quality than online, but it's just better resolution, better sound quality, So I highly recommend coming in person because I was just doing my first in-person lecture for the 1MD3 class because it's a first-year class, right? I did that like a couple of hours ago, and I was reviewing the footage briefly, and it's definitely like I'd say it's better quality than Teams, really, but it's not as good as the stream because I have a nice fancy microphone and stuff, but will I be doing any epic edits since I'll be posting them after the lecture instead of live streaming? No, I'm going to probably not edit them hardly at all. We'll see. I might slap a title. I might slap like a title card on them or something, but in general, I'm not going to be doing much to them. It's like that video editing takes way too much time. Yeah. Oh yeah. Midterm. Let's take a look. Get a mic for my shirt. Yeah. They're expensive though, Like the cheapest one that you should that would work probably is like $200, so Maybe at some point I'll upgrade. But the other thing about miking me and having that as the audio input is that it loses anybody who's asking a question. And, you know, it's never really that strong anyway, but, you know. Where is it? Test is in the week of March 6th. So we haven't set a date, but it's 2 weeks after reading week. More music in the lecture hall before class starts? Yeah. I mean, you guys could play some if you want, but when's the midterm? Well, we haven't decided yet what day in that week it will be, but make the university pay? If this is how it works, right? If they buy you equipment, they expect it back, and I would prefer to just own my equipment, so. And, you know, we get along reasonably on I like to get by on my own steam when it comes to these sorts of things. I prefer to own the equipment myself. You know, but more music, more like Moore music. Whoa, that's the first time I've heard that joke. That's the first time someone's made that joke about my last name. So, yeah. Yes. Yeah. Yeah, anyway. So, it is my full and complete intention to get through this entire slide deck today. So we need to get moving, because we need to keep moving, eh? So we were last talking about the manner in which memory mapped I/O can be interacted with, and the yeah. You know, so memory mapped I/O, right? You've got your memory cells. Each one of those bits is wired up to, you know, one or more control circuits that are controlling the manner in which the output is configured and the actual value that's being driven there, right? Yeah. So the next few slides go through a few of the individual things that the memory maps to, and I'm just going to go through them quickly. There's a clock enable, right? There is a peripheral clock on the board that you can enable through RCC AHB2ENR. You know, one is enabled, 0 is disabled, as you might expect. We're going to be talking a lot about timers and clocks in the next lecture slide, or in the next set of lecture slides. So I'm going to leave most of that, but yes, Ethan, I was being just a smidge sarcastic. Just a little bit sarcastic. So we're going to leave clocks for when we're talking about timers and clocks, which we might even get there at the end of this lecture. But you can enable one. So, you also have mode R. So this is what it looks like. You can see it's been broken up. You got 16 pins and 2 bits per pin, right? So this kind of answers the question. Each GPIO port has 16 pins. So pin 0, pin 1, pin 2 are all lined up. You get two bits per pin, and that occupies 32 bits. Nah, it's okay, Ethan. You're doing fine. You know. So remember that, you know, remember that we have to, each pin we select between input and output mode, right? We can also have alternate function mode, which is specified elsewhere, and we have analog mode. So really, input mode and output mode are the most useful and interesting ones to us at this point. But this is what the register looks like, and this is how you set it, right? So if you wanted to set pin 4 to general purpose output mode, you would skip 0, 1, 2, 3, and you would focus on the mode of pin 4. You would set this bit, you would set that bit to a 0 and a 1, and there you go, configured. The output type register, you configure between output push-pull and output open-drain. It only takes 1 bit to select between those options. So in contrast to the mode R register, the output type register only actually uses half of the register, and this is actually very similar to the output data register, ODR. So each one of these, bit 0 is pin 0, bit 1 is pin 1, etc., etc. And then we also have this interesting idea, which I don't think this is the first time we've seen this idea, that bits 16 through 31 are reserved. So what reserved means is while these things exist physically in hardware, there is no they have not been assigned a purpose, right? You can think of it like a region of unused memory. These regions of unused memory are often included because sort of when you're producing successive designs of something like an ARM architecture, it's useful to leave space in, the memory map for things that you might add later. That will be one use of reserved bits, and sometimes it just doesn't make any sense to use them, in which case this is basically like these bits don't do anything. They're reserved for other purposes, basically just means safe to ignore. So but all this is configured in software like C. So when you write the bits to these individual memory cells, you will be doing that in software. Using the methodology, which is explained here in our previous class, or using the API. So good. So in addition to that, we have the output type register, which looks very similar. Oh, wait. Where am I talking about? No, I'm sorry, yeah. Sorry, I thought this was a different one. So the output type register, of course, you can set it between push-pull and open-drain, which are things we've talked about. 0 and 1, obviously. So essentially everything is fully configurable. Right? So let's consider these two LEDs that are on this board right here. If we have PB2 and PE8, which are what these guys are connected to, under push-pull configuration, setting it 1 will turn this high. Setting it 0 will turn it low. So, fine. Under open drain configuration, setting this output bit to 1 sets this pin to high impedance, whereas setting it 0 sets it to low voltage. So, of these 4 categories, which one of these makes these LEDs work? Answer, it's high. Should we focus on the code you have at the bottom in red? I'm still having a hard time in understanding line by line what the code does. So that'll be because it's it's a lot of bitwise operations, right? So yeah, I can go through it. So in this case, if we want to set, for pin 1, if we want to set this bit, right? We go to the RCC register. We select the So this is like the pointer operation here. It's the same thing as structure access, like structure field access combined with pointer dereferencing. So that's the accessing of this field, and it's or equals the current value. So this is actually toggling it, right? I think no, that's not it. Does it say where GPIO B enable, IO port B clock enable? All right. Oh, all right. Yeah, to be honest with you, there's stuff going on here that they haven't put on the slide, so I'm not sure what they're... And there's no reference to that in the textbook, I don't think, so I'm not sure what's going on there. But I can explain what these guys do. What is high Z? High Z means high impedance. So you can think of it as disconnected, although you can't technically disconnect anything if it's... Like, technically speaking, it's not disconnected if it's a transistor, because it's like nothing is physically separating. But a high impedance state means that like there's a high enough resistance there that it simulates an open connection, right? Because, of course, you know, air is not without some degree of conductance, so it has a very, very high impedance, which is why it's a fantastic insulator. So, for this guy, we've got GPIO port B, the mode R field, and equals not 3 moved to the left by 4. So 3 is, of course, 1 and 1, right? We move that to the left by 4, fine, you know. And then we not that, which sets it 0, right? So, and so 0, so whatever is in there, when you perform AND with it, the zeros will clear it back to 0. So that's the purpose of this piece of code, is to clear the existing mode, because you should clear it before you set it, because, you know, this OR operation, if it's already set, you won't get what you want out of it, right? So, and then we just, in order to set it to general purpose output mode, you know, if you were to set that in pin 0, it would be 1. So, since you're setting it at pin 2, you shift it down by 4. There you go. Is the GPIOA example from last class supposed to be 2 bits per pin or 1 bit? So ODR is 16 bits. So the ODR example that we're doing here would resemble this one, because it's 1 bit. Because you only need 1 bit to output something, right? How many pins are there? Did we ever figure that out? It's 16. There are 16 pins. 16, which is why we can have these guys occupy 2 each, because we have 32 bits in total. Yeah, good. For O-type, all we have to do in order to set this to 0 is to clear the bit regardless of its state. So we create 1, we left shift it by 2, and then we take the logical not, or the bitwise not of that, and it with the O-type, with the existing register, and that will set it to 0. There you go. You can also figure out, like, do it in binary, like, you know, 0B, 0, 0, 0, 0, 0, 0, and then 1 where you need it. You can also do it that way, but, you know, this is a bit more numerical, and it doesn't take as much time, and it's less likely to result in an error because you've miscounted the number of zeros. If there are 16 pins, why are there 32 slots for O-type where it says 1 bit for each pin? Well, because the register is of a fixed width, right? Every single memory cell is 32 bits, and these guys are no exception, right? When you're programming, when you're dealing with memory at this level, you absolutely need to respect word boundaries. That's like one of those little abstract pieces of, you know, that's one of those design principles with respect to memory management that's like everybody does it, but nobody talks about it because it's kind of just assumed. Like, if this is the output type register and all registers are 32 bits in size, then even if this register is only actually using 16 bits of it, the other bits are still in that register. We're not going to try to use them for any other purpose. We have more bits than we need, so we don't need to crunch things and compress things down to that level, basically. It's like memory might be expensive, but address space is cheap. Is another way of thinking about it. So, good. So, if we wanted to set this guy, PB2, we just take our output data register of GPIO port B, pin 2, drive it high, bing, bang, boom. So when it says there is 1 bit for each pin on the slide, it means only 1 bit is being used, not there is only 1 bit available per pin. Well, okay, I see the source of the confusion. Yeah. So first, take this first part of the sentence to mean there are 32 bits in total, half of which are reserved, half of which represent data bits. Because that's the case, there is only 1 bit used for each pin because there are 16 pins. So that is to contrast this case, where we have the same size register, 32 bits, but we still have 16 pins, but we have to have 2 bits per pin to be able to configure these 4 different modes. So we actually use the entire register to represent data for all of these different pins. Does that make sense, David? Good. Hopefully. I hope you said yes. So, in general, so if you run all of these statements together, you eventually are able to output a 1 to turn on the red LED, because we have cleared the mode bits, set the mode to output, selected a push-pull type output, which is necessary because in a high impedance state, this pin will not be able to drive any voltage through the LED, right? Open drain does not provide voltage. Only push-pull provides voltage. So you have to configure it in push-pull mode. Right? Awesome. Thank you. So, and then once you have configured that, you set the output to 1, and on goes the LED. Cool? Let me just see if everybody's good so far, because we're going to move on to a different example. Oh, pardon me. I had forgotten how much fun it was to teach a class in person. If anybody has any questions, can I go over the LED code one more time? What kind of? Okay. So, first, we enable the clock port for port B. I don't know why, because they didn't really explain it, and this isn't in the textbook, so I don't know why. But we clear the bits that control the mode of this pin. We then set the mode to output in the same manner, like all of these statements are the ones from these slides, right? So, you know, we clear the bits, we set it to 0, 1. Good. We then set the O-type bit to push-pull, right? And then we actually drive a 1 to the 2 pin of the ODR register, and then that turns the LED on. So perhaps I should make more clear what, like, my expectations of what it is that you should learn from all of this are. First, it would be a good thing for you to know what these registers control, right? I'm not going to quiz you on stuff like, you know, 0, 0 is input mode, 1, 0 is alternate function mode. Like, if it's the type of stuff that you would look up in a table if you were actually building a system, I don't really think that's not really a good demonstration of your understanding of the subject, right? Because if you were a real engineer working on a real system, you would have the table, right? So that's not really what I'm going for here. I'm going more for like I'm going more for like the conceptual level, right? Still not sure what each register does. Well, each one of these is wired up to a circuit that controls like whether or not the output pin is configured in push-pull mode, or as an input or an output, or an, all of the options that we've been talking about this entire lecture. This is how you control it, because it's memory mapped I/O. The registers themselves, like, you write into the register using your normal CPU write operations, and those data are carried down to the circuit, which configures itself according to the circuit, and, of course, drives the output that's requested by the CPU. So I'm not sure I can make it much clearer than that. At least not on a first pass. Oh. Yeah, that's just names that they've given it, right? So yeah, it's like you've got, yeah. They're kind of like there are some ones that are more important to know than others, right? Like IDR, input data register, ODR, output data register, O-type, pull up, pull down, that sort of thing. But we need to keep moving, because I'm determined we're going to finish these slides today. So let's consider keypad scanning, right? So this is an application of general purpose I/O. So let's say that you had a keypad, and like a keypad is a series of push buttons, right? There's like a less smart way and a more smart way, I guess you could say, of configuring or wiring up a keypad. I can't end the vote. What's end poll? Thank you. One way you could do this is you could wire up each one of these things to one GPIO pin. But as we've discussed many times, minimizing the number of like minimizing the amount of everything that you need is like the name of the game in embedded systems. So there's a way of configuring this thing so that you only need so that you only need 7 pins. We're going to have 4 of those be output pins and 3 of those be input pins. And using 4 output pins and 3 input pins, we can actually read any key presses on this keypad. So, this is how this thing is wired up underneath, right? So, oh, I'm sorry, I got it mixed up. The input ports are at the bottom and the output ports are at the top. No N key rollover. Yeah. Not unless you do it in software. So, these push buttons are represented by these sort of contact, these closed. I don't know if you guys have seen this symbology before, but like think of it as if it were a just like a latch switch, except that indicates that this latch is being switched by a button, basically. So we've got our output ports and we've got our input ports. So these lines do not, these wires do not intersect, right? So when, for example, 5 is pressed, the contact is closed between pin C2 and pin R2, right? So, essentially, we use an algorithm in addition to the pins in order to scan the keypad to see if a button is pressed. And if you scan it quickly enough, you will be able to catch any human button press because we are much, much slower than a computer is. So the general algorithm is we need to find out which row it's in and which column it's in, and then we go back, then, you know, basically we scan through all of these things. If you are doing input instead of output, don't you need to set O-type? You don't need to set an O-type to anything, right? Yeah. Like, output options are only relevant if the pin is configured in output mode and vice versa. So initially, we set zeros to all of the output ports, and we are receiving ones from all of the input ports, right? Because, again, we assume that the input ports themselves have no current draw. So that means that these lines would have reached the positive 3.3 volts despite the existence of the resistor, right? So, we have no key presses. Let's imagine that key 0 is pressed, right? That contact is closed. So, this high signal now travels down to R4. So, this would trigger an interrupt, right? The keypad scanning algorithm would be initialized by a 1 being received on any of the output ports, right? So that starts you off on the scanning algorithm. So we already start off with some information, right? So, because we're outputting 0 here, right, that 0 pulls this guy down, right? So the input port reads 0 down here, right? I think I got my output port and my input port confused again. I'm sorry. So because, yeah, sorry. I got my bits flipped. So when you close this contact, this guy is reading 0 because it's directly contacted to this guy, which might be in, like, you know, open drain or something like that. So we're reading 0, right? That any one of these guys being set to 0 initiates the keypad scanning algorithm. So we can start scanning. We already know what column the button that's been pressed is in, because whichever of these pins goes low, that's the column you're in. But we don't yet know if that's because, 0, 8, 5, or 2 was pressed. We can't tell yet. So this is what we do. We scan through the rows. So we set all rows high except for the first one. If that makes... so whichever of these configurations results in the pin that we're looking at going low again, that's the row that we're in, right? So, for example, if we're setting R1, R3, and R4 high, right? R4 is like the one that's connected, obviously. But so it's driving a 1. So C2 is going to read a 1, right? But if we send it a 0, basically we're back into our original configuration, regardless of what the other pins, what the other rows are doing. So by process of, by scanning and watching and waiting for that pin to flip, we can determine which row that key press is in. And once we have a column and a row, we have our button figured out. Cool? So far so good? Hopefully? So, we can conclude the key press is located at the second column and the fourth row. Good. So we want the row and column to have 0. Well, it's not so much that you want the row to have 0. You set, like, your exit condition, or your condition for determining the result, is definitely that you return to a state where the input port that you're watching returns to 0. So you are waiting for this guy to go 0, but it's correct to think about your output ports as the things that are under your control. So, so you scan each of them to see which one has an effect on the input port that you're watching. So maybe that makes things a little more clear. When we have identified which row the pin, the button is on, both the column and the row will have gone 0. But we don't know which one until we've scanned, until we found it. Awesome. Good. So, one thing that you have to be kind of wary about, this is just collecting which button was pressed. Doesn't have anything to do with a password or anything. No, not at all. Yeah, so to scale things up from here, the way that this would actually be used, so you would punch some buttons on this thing. So you would perform several keypad, you would perform several keypad scans to get, like, say, a 5-digit passcode, right? The software obviously stores the individual digits as they're being returned. There would probably be an LED somewhere on the keypad that would indicate, green for pass and red for I'm not letting you in. Pardon me. If you imagine it on a door or something, right? So what then would happen, likely, because that's like the way things work now is different from how they used to work. Likely this peripheral is also connected up to some kind of networking service. It would then produce something like an SQL query that would run to something like a database, which would scan for, like, is this a valid code? You know, some kind of centralized database for your organization. And then if that query returns, yes, this passcode is a valid passcode, then, you know, the LED lights up green and signals are sent to the locking mechanism to disengage, and you can open the door. But yeah. The keypad itself then isn't an embedded system, I'm assuming. It's just the mechanism on which the passcode is input. Yeah, no, the correct way to think of the keypad is as an I/O peripheral to an embedded system, right? So the keypad itself is like this is, I think this is an actual physical, this is a physical picture of one, with the pins at the bottom. Although I think so. So yeah, like these pins would be plugged into a GPIO port. So would the keypad be pull-up or a system of pull-ups? So, well, that's what these guys are up here, right? These are the pull-up resistors. So, there you go. So, one thing to be careful with here, and this is like an this is a real world example of when you should use pull up, pull down, and open drain configurations, right? So let's imagine that we're using, and you know, you can probably figure this out from the diagram. If you've got it configured in push pull, right? If somebody pushes two buttons in the same keypad, or in the same column, and it's using this algorithm, you'll end up with a short circuit, because one pin is driving a high voltage, the other is connected to ground, and there's no resistor anywhere here, right? So this is a short circuit that will, you know, probably fry your board, and you'll have to get a new board, but the keypad might be fine. I don't know. Depends on how simple it is. But yeah, so that's not a situation that you want. But remember, folks, these are pull-up resistors. So if these guys are if these guys are configured for open drain configuration, high impedance on here in this configuration will be a high signal as read by the input, right? So so something like this, you actually do have to worry about putting it in push-pull versus open drain. This can create a short circuit. So if you're if you're ever feeling sufficiently mischievous, you can always, if you ever encounter one of these 12-digit keypads, you can always push two of the buttons in the same column at the same time. See if it's been configured in the correct configuration. Yeah, no. That's, yeah. There's no such thing as a stupid question. So, so we just have one more thing to talk about then, and that's hardware debouncing. Hopefully this won't take too long. So switches, right? Switches are mechanical objects. You're actually closing contact between metal surfaces. Now, are any keypads like that on campus? Oh, probably. I've not tested them, and I do not endorse the destruction of university property, even if you know how to destroy it. So I want you to imagine in your minds, right? Two electrical contacts with a bar with 2 electrical contacts above it, right? Somebody pushes the button, the 2 contacts snap together as long as the button is pressed. When the button is released, the spring loading in the button opens the contact again, right? Because things in electronics land are happening so quickly, the embedded system will be able to read the very, very brief period of these contacts bouncing as they close, right? Like, I don't know if you guys know this, but metal is actually kind of bouncy, as a material, its properties, because it's because it's a crystal structure, the thing deforms and then snaps back into its original, metal is what's that called? It's not ductility, it's not malleability, it's it has a certain elastic property past, a certain point. So so how does this, why am I telling you this? Why does this matter? When your electronics operates fast enough to be able to pick up this bouncing, you can actually read incorrect signals from switches because of this bouncing effect. So one of the things that we have to do is debouncing. Surface tension? No, it's elasticity. Y'all took materials last year, right? Well, surface tension is a property of certain materials, like water. Water is a material. Anything material is a material, right? So anyway, so this is a oscilloscope reading from an actual button that had actually been pressed, and you can see that we actually get a pretty big spike, which could be interpreted as a high signal. So we'd get high, low, which could look like multiple button presses, right? Bounceability. I like bounceability. Young's modulus. Thank you, Omar. So basically, especially in systems where the number of key presses is important and not just that a key is pressed, right? In a keypad example is a perfect example because the number of numbers that you enter is also important. This can really mess you up. So there are a couple of ways to fix this. Number one, the simplest way is to just put an RC circuit on it, right? You guys did low-pass filters, I assume? Hopefully you guys did low-pass filters. The other way you can do it is, you can basically do this in hardware or software, right? A low-pass filter filters out high-frequency noise. So it's sort of, you would get it coming down more gradually, and it would sort of hiccup a little bit as it went, but it would become a much more reliable signal. Even this big spike here would just kind of pull it up a bit, but it would just it takes the edge off of all of the peaks. The other thing that you can do is you can wait in software. It's basically kind of a wait and see method, right? It's you register the change in position, right? And then you wait however many milliseconds, and you read it again and you see if it's still in that new state, right? But yeah. So solution B, read the switch after a sufficient delay to allow the bounces to settle down. So that's solution A. Solution B, reading periodically and using a counter as a filter. Reset the counter when the signal is unpressed. Counts up if pressed. If counter is greater than threshold, the contact has stopped bouncing. So that's like, so it's like, you know, counting how many clock cycles it is in its you know, up or down position. What kind of circuit was the graph shown from? Was it a simple RC or a low-pass filter, or was it something else that why its waves were weird? This guy, this is unfiltered, right? So this is what the mechanical switch will do if it's got no filtering on it whatsoever, right? Which is why we need the filtering, right? Of the two of these, I would say RC circuit is probably the easiest solution. It's also the fastest solution, right? It might, like an RC circuit might impact you. It might delay the signal propagation for, you know, like, you know, like 100, 200 nanoseconds or something like that. But, you know, it's not really a big deal. Normally when you're having to wait for these software, for these software counters and that sort of thing, normally that increases the amount of delay you need by quite a bit more. But, you know, it can also, like, when you're introducing RC circuits, you're actually introducing actual hardware, whereas software is the cheapest thing in the universe. So, yeah. Are there any questions about that? Yeah. So this is like, this is a very simple circuit, right? It's like plus 5 volts, resistor, switch, ground, with an oscilloscope testing the voltage. Or I guess the switch would be, yeah, it would be testing the voltage across the resistor. What's the threshold in the last point supposed to be? Well, it's kind of arbitrary, right? It depends on how good your switches are. If you use more expensive switches, then you don't have to threshold it as large. But, you know, basically that's one of your little points. That's one of your little engineering control points where you can sort of crank it up and down and see, wait until you get something that works. Like, these types of parameters are often, like, worked out on prototypes and stuff. Like, if you tried to produce some kind of theoretical threshold, it doesn't matter how good your theoretical reasoning is going to be about what that threshold should be. You're always going to be wrong when you actually build the circuit, you know? So, to some extent, it's good to have, like, a ballpark, but, like, you know, like, you might say something like, well, I feel like I would probably have a pretty good reading after 300 nanoseconds or something like that. But, you know, who the heck knows, you know? You would actually test the threshold to make sure that you weren't getting any bouncing after 300. And if that was too much of a propagation delay, which, you know, probably it's not because it's 300 nanoseconds, but it might be, you know, you could like crank it down, make it, you know, fine tune it a little more. You can find a good place for it, you know. But again, it's also going to depend on like how your switch has been. I'm sorry, I keep hitting this thing so much. How your switch is going to has been constructed is going to affect it. Like, you know, the quality of the parts, like the manner in which it's pressed can also have a big impact on this. Like, if this switch has been pressed by like one punch man in a punch, that's going to be one that you're going to get one type of signal out of that. But if you have like it pressed accidentally by a chihuahua that is currently scared to death of a gigantic tarantula, like, that's going to be a completely different waveform, you know? I guess you don't really have to worry about dealing with One Punch Man, because he would powderize the entire embedded system, and that probably means you don't have to worry about that test case. Engineering. Good. Well, if there's no other questions, and I see people are kind of leaving, I'll leave her here for today, folks. Thank you very much for your time and attention, and I can't wait to teach this class in person next week. Take her easy.